we are going to do is, since now we have reviewed the three postulates from the continuous time sinusoids related to frequency, we look at the discrete time sinusoids. Discrete time sinusoid can be defined as a function of an independent variable, small n. You may note that in continuous time it was small t. The unit of small t was seconds. Here small n is samples, and samples are counted in terms of integer values like 0, 1, 2, 3 and so on. And a discrete time sinusoid, x is a function of a small n instead of t because the signal has been sampled. We will look at the sampling process at a later stage. And the definition of a cosine in a discrete time is almost the same. It has an amplitude a multiplied by a cos function, and omega d, small d in subscript, represents that this omega is for the discrete domain, and we will see what they are at a later stage when we study sampling. In continuous time this function was omega t. Here in discrete time it is omega n, and small d is just to indicate that this is a discrete time frequency, plus phase, and the phase here is we are representing it instead of theta, we are using a signal phi. Again, since we are interested in looking at the frequency, what we can do is set up value of a as 1 and the phase as 0, simplifying this expression into cos omega dn. And because omega is equal to 2 pi into frequency, we can also write this as cos 2 pi small fd into n, where small fd is again the frequency for in a discrete time domain. The units of omega d are radians per samples. You can note that while in continuous time these units were radians per second, here the units are radians per sample because the independent variable is now changed from small t to small n. And similarly the units of fd, small fd, are not cycles per second but cycles per samples. Okay, we will look at the concepts of frequency in discrete time sinusoids now, and we will take them one by one. So I'm skipping this slide for now and moving on to the postulates directly. Okay, so postulate 1, in the discrete time sinusoid it says a discrete time sinusoid is periodic only if its frequency is a rational number. Now we know what a rational number is. Rational number is a ratio of two integers, is a fraction of when a fraction with a ratio of two integers. Now the interesting part to note is that for a continuous time sinusoid there is no condition of periodicity. Every continuous time sinusoid is periodic with a periodicity capital T, and to think of a condition that a sinusoid can be there which is non-periodic is slightly different and is not something we have studied before. But the postulate 1 of discrete time sinusoid is saying that yes, they will be periodic, but if their frequencies are a rational number. So let us now look at how this works. We know that a discrete time sinusoid is given as cos 2 pi fd n, small n. So what we are going to do now is to add a capital N with a small n just as a periodicity notion, just like in a continuous time sinusoid, we have small t and we add capital T along with that to indicate periodicity. So we are doing exactly that. In discrete time, the periodicity will be given in terms of samples, not in terms of seconds. So that's why we have taken capital N as the periodicity in terms of samples. So for example, we can say that a discrete time sinusoid is periodic with capital N is equal to 12 samples. So it means that this is a signal which repeats itself after 12 samples of interval. So here what we have done is to add capital N as a periodicity in terms of samples with a small n. So now this becomes cos 2 pi ft small n plus capital N. We know the trigonometric relationship of cosine alpha plus beta, which expands into cos alpha into cos beta minus sine alpha into sine beta, and we can apply this expression on this cos 2 pi fd small n plus capital N function, which will expand into cos 2 pi fd small n into cos 2 pi fd capital N minus sine 2 pi fd small n into sine 2 pi fd capital N. Now, in order to convert or equate this expression with cos 2 pi fd small n, which is this, so in order to prove periodicity, what we will have to do, if we look at this expression again, then cos 2 pi small fd n is here. We would like to make this function as 1, as equal to 1, and this entire function equal to 0. So if we make this function as 0 and this function is equal to 1, then we will be left with cos 2 pi fd small n, and this expression will equate with cos 2 pi fdn, thus proving the periodicity property. But now let's look at how to make this expression as 0 and this expression as 1. So we note that this is cos 2 pi small fd into capital N. So 2 pi fd capital N. Fd capital N is a function which is being multiplied with 2 pi, and if you want cos 2 pi into something as equals to 1, then this something needs to be an integer value. We know that cos of 2 pi into any integer will always give us the value of 1. So from here we are observing that the condition which is coming back to us is that fd times capital N should be equal to an integer if we want this expression to be equal to 1. Leaving this aside, now let's focus here. Here there are two expressions, fdn, because small n is variable here, so we do not expect much to gain from here. But here it is the same function, sine 2 pi fdn, fd capital N, and fd capital N, if again it becomes an integer, then sine 2 pi times an integer will be 0, and 0 multiplied by any function here will still be 0. So from both sides we are getting the condition that if we want this entire equation to be equal to cos 2 pi fdn, then this is possible only if fd capital N is equal to k, where k is an integer, or fd is equal to k over n, where k, as we have just noticed, that this will be an integer and capital N is also an integer, thus making fd a ratio of two integers, that is a rational number. So we go back to the postulate 1, which says A discrete time sinusoid will be periodic only if its frequency is a rational number. Now this is a very interesting observation because this is against or different from what happens in continuous time. In continuous time, every sinusoid is periodic irrespective of whatever its frequency is. But in discrete time sinusoid, it will be periodic only if its frequency is a rational number. So let us now look at an example.